Hello everyone. In this video we will talk about the concept of Fourier descriptors, and Fourier descriptors is one of the boundary descriptors. So in order to proceed along the discussion, I have considered a Cartesian plane over here where the x-axis is along the horizontal direction and y-axis is along the vertical direction. And I have several points along the boundary, and each of the points are given with a coordinate pair x0, y0, x1, y1, etc. up to the last value will be xk minus 1, yk minus 1. That is, we are traversing the boundary along the clockwise direction. So the coordinate points are x0, y0, x1, y1, etc. up to x capital K minus 1, y capital K minus 1. Okay, that is, we have in total capital K points. Each of these points can also be written as sk equal to xk comma yk. That is, these k are small letter k which represent a general variable, and we can also write sk as sk equal to xk plus j yk. That is, we are writing the x coordinate as the real value and y coordinate as the imaginary value, and we are forming a complex number. So by doing so, we have converted a 2D parameter into a 1D parameter. That is, each of these 1D parameter is a complex number. As sk is a complex number, we can find the DFT of each of these points on the boundary by taking each of these points as a sequence of a signal. Okay, so we can find the DFT of the value sk. Okay, so the discrete Fourier transform DFT of sk is defined as a of u equal to sigma small k equal to 0 to capital K minus 1 sk e raised to minus j 2 pi by capital K small k u. Okay, so here the k represent the subscript of the input quantity sk and u represents the subscript of the output quantity a of u. As the value of k ranges from 0 to capital K minus 1, the value of u will also range from 0 to capital K minus 1. So we will have u taking values from 0 to capital K minus 1. Okay, so as we have a of u for all values of u from 0 to k minus 1, the complex quantity a of u are called the Fourier descriptor, where you have to find the values of a of u for u is equal to 0 to capital K minus 1. Now the inverse Fourier transform of this quantity restores the values of sk. That is, we can find the values of sk from a of u by finding the inverse discrete Fourier transform of a of u. So the inverse discrete Fourier transform IDFT is defined as sk equal to 1 by capital K sigma u from 0 to capital K minus 1 a of u e raised to j 2 pi by capital K k u. Okay, so as we have capital K values for a of u, you will also get capital K values for s of k. So the values of small k varies from 0, 1, 2, etc. up to capital K minus 1. Suppose that instead of using all the coefficients of a of u, you are just using only the first p coefficients. That is, the values of a of u are set to 0 if the value of u is greater than capital P minus 1. That is, we are considering only the first p values. and we are setting the rest of the values as 0. So the new values of sk will look like this. That is, I'm writing it as s hat of k equal to 1 by capital P, because we are considering only capital P points, sigma u from 0 to capital P minus 1 a of u e raised to j 2 pi by capital P k u. Okay, so the difference in this equation is we are taking only the first p coefficients of the signal a of u, and we are removing all other values by setting it equal to 0, but the value of small k still ranges from 0 to capital K minus 1. Okay, so that is, we are taking u from 0, 1, 2, etc. up to capital P minus 1, but we are calculating the values of s hat of k for k from 0, 1, 2, etc. up to capital K minus 1. What we are doing is we are removing the high frequency components of the signal A of u. By removing high frequency components of A of u, we will be missing some minute details of the boundary, but the overall structure of the boundary will be preserved. If you want more precision along the boundary, then you have to take all the coefficients of A of u, that is, you have to set P equal to capital K. If you can compromise some precision along the boundary, then you can reduce the number of A of u's that you are taking, that you can remove some values from the end of the signal A of u. Now we will look at one example that shows this aspect. Here I have shown a diagram. So in this diagram, the first one is the boundary of a human chromosome, and which contains around 2868 points. And suppose that we are describing this particular boundary using a Fourier descriptor, and in order to recreate the original boundary, we will be finding the IDFT. But during the process of finding IDFT, instead of taking the 2868 points of the DFT signal, we are considering only the 1434 points. Then if you reconstruct the boundary, you will get a boundary like this. And if you reduce down the numbers from 1434 to 286, 144, 72, 36, 18 and 8, these are the boundaries that you can recreate. Okay, so you can see that as we omit more and more coefficients from the end, more precision from the boundary is lost. Okay, so at the end you will be just getting a structure which look like the chromosome but doesn't have any minute detail. This structure does not have that much resemblance with the original structure that we have in the beginning. Okay, so this is the idea of using Fourier descriptors as a boundary descriptor. I hope it is clear. Thank you.